Now let's look at the next example problem, matrix block sum. So we are given an m by m matrix and an integer k, and you're asked to return a matrix called answer, where each of the answer ij is the sum of all the elements in the matrix for k row to the left and k column to the left, k column to the right, and k row on top and k row below. So here I use this to illustrate the value that should be put in here, the answer for this cell. We go 2 row and k when k equals 2. So when we go k rows up, but there's no k row, there's no row up, which is fine. So we go 2 rows left, so there's only 1 row, so we will reach the left boundary. And then we go 2 row right, 2 column right, so then we'll reach this part, and 2 column down we'll reach this part. So all these 12 cells highlighted these other cells whose sum will be whose number will be added up to get the answer for here. So that's what this question asks us to compute. So again, encourage you to pause the video and try to solve the problem on LeetCode. So here is a brute force method to do it. So we get the size of mn, and then for each of the answer array ij, what we do is we'll loop through all the rows and columns that are in the range. So we'll start from I minus k and go up to I plus k. However, we don't want a negative value. We don't want to step outside the boundary. So the starting position is max of 0 and I minus k, and we don't want to go outside the other direction. So we stop at m minus 1, the mean of m minus 1 and I plus k. Similarly, we do that for j. So this works, and in fact, this is accepted in LeetCode, even though it's not very efficient. So what is the time complexity for this? So the complexity is m times n times the k squared. So if k is fairly large, then this is essentially a quatic, so n to the 4. So if m and they're all similar size. So how do we speed this up? So we use a technique called 2D prefix sum array. So in topic 1, we covered the prefix sum array and the difference array, and for one-dimensional. But the same concept can be generalized to two-dimensional. It's just that there's a little bit extra complexity that we need to deal with. So given an array aij, and the prefix sum array is defined as the sum of all the arrays that are kind of ending at the current cell. So let's take a look at the concrete example. So if this is my original array, then in the prefix sum array, the element for this position will be all the values in here. So the first 2 row and 3 column. The element here should be the sum of all the element, all these 6 elements. So given this original array, I can compute a prefix sum array, which can be computed in time linear in the size of the array. So once we have the prefix sum array, we can use that to help us compute the range sum, to help us compute any of this rectangular matrix, sum of rectangular matrix efficiently, which is what this question need, right? So here we're trying to compute the sum of a rectangular matrix in the original matrix. So we are trying to make that step efficient. So these slides explain the intuition. So if I want to compute the sum of this 4 yellow highlighted number, So I can use the prefix sum ending at here, so which is the sum of all the blue highlighted number. So if I include that, then I'll be including too many things, right? So because I don't want the two left column, so I need to subtract those. So then that can be, I can subtract the prefix sum ending at this 12 here. That will be the sum of this 6 number. So then I got rid of this left part, but I still have this 3, 4 here that I don't want. So I can subtract the prefix sum ending at here. But then what happens is the value here, 1 and 2, are subtracted twice, here and here. So I need to add it back. So any rectangle sum can be computed using 4 elements in the prefix sum array. So it's the big one, subtract this left one that we don't want, the top one we don't want, and then add this one here back. So given a prefix sum array, then we can compute any range sum in constant time. So in 1D we just have a subtraction. We don't have this extra subtraction and addition. So another concept is similar to difference array, is this different matrix. So this is not needed for this example problem, but this is needed for the homework problem, rectangle counting. So essentially you need to understand this to do that problem. So suppose I want to update this array by adding 2 in this rectangular region. So I want to add 2 to every cell in this rectangular region. When this region is large, then this update can be slow. So I need to update all the cells. But instead of updating this matrix directly, I can update a difference matrix. So what happens is I can do the update like this. I only update 4 cells. And when I have many updates, I will just keep doing this update. Every update translating into updating 4 cells. After all the updates are done, then I compute the prefix sum matrix of this difference array, and then I get what I want. So look at this example. Suppose what I want is add 2 to these 6 cells. So so then remember this is difference array. So our effect, we want to okay. So the adding 2 here, when we consider prefix sum, the effect will be all the cells from here to here and from here to the corner will be let me create the point. Okay, so all the sum from here to the corner will have a +2 to it. So then this 6 has a +2, but then there are also here where I don't want +2, there's also a +2. So I do that by having a -2 here. So then the when I add everything up doing prefix sum, here it becomes 0 because it has +2 -2. Here it also becomes 0, have +2 and -2 for this 2D prefix sum. So similarly here I don't want update, so I have a -2 here. But then anything in this part will have a -2 if I don't do other things, because it's +2, -2, and -2. So I need to do a +2 to correct that. So so you can manually verify. So given this array, if you compute a prefix sum array on here, so for every cell you compute the sum of all the values starting from beginning ending at here, you will get exactly this. So if I have another update, say +3 to this region, then I will need to do +3 here, -3 here. I guess this is outside the matrix. I don't need to do the minus that. So the boundary condition need to be a little bit you need to check for the boundary condition. So if it's in the bound, then you don't need to do this -2 +2 thing. So this is a range update can be made efficient by maintaining difference array, and you benefit when there are lots of update, and after the update you want to answer the queries. So let's look at the more efficient version of this problem, metric block sum, that we use the prefix sum array. So to get higher efficiency, there will be more code. I think this is for computing. Yeah, this is for computing the prefix sum array. So this is computing the first row. So from the matrix MAT, I compute the prefix sum. So the first row, and then the first column is computed this way. And then for the rest of them, to compute the prefix sum, yeah. So this code is one way to compute the prefix sum. So let's illustrate. So if I want to compute the prefix sum up to here, so and I have already computed all the other prefix sums. So what do I do? So I can use the prefix sum ending at 13. So then I can add that value. But then I'm missing this 4 and 9. So I can also add the prefix sum ending at 9. So, but then the part that ending at 8, this corner ending at 8, will be added twice. So I need to subtract that. So that's what this code is doing. So it uses the prefix sum at the top and the prefix sum to the left, add them, and then subtract the one to the left corner, and then it add the element of this at this position. So this is not the most efficient way of computing prefix sum. So in fact, if I use an auxiliary 1D array to store all the maybe do I need the 2D auxiliary array? No, yeah, I don't need that. I think, yeah, I can use I can maintain a rounding sum for this row, and that will work. So for example, to compute this 13, I just need to have the prefix sum ending at 8, then add the sum on this row. So because I'm going through this row one by one, I just need to maintain this rounding sum and then add it to this. That actually, it's I think it will be slightly more efficient, but than this code. But this code again illustrates this pattern that we see. You add the two things, and then there are things that you added too much, and then you need to subtract to compensate for that. And this shows the code to use the prefix sum array to construct this block sum. So I don't think there's anything that's yeah, I don't think there's anything to I wrote the code in I guess slightly try to be a little bit more efficient, but at the cost of slightly less easy to understand, because there's a lot of boundary conditions, whether there is something outside. So I start with the just sum at the ending position of I and j, and then depending on whether the beginning position is outside the array or not, if the beginning position is outside the array for one direction, then I only need to consider the other direction. So when they are both actually outside the array, then this value it is. So I don't need to do update. I'm adding actually from the top left corner. So this just the code just deal with these conditions. If you've written this, if you try to write the code, it should be straightforward to understand what this code is trying to do.